So I'll be talking about coordination in software-defined networks. So, SDN has been presented at NSDI for at least the last 6 years. But just to quickly go over what SDNs are, we have, or what I'm talking about, just so we agree on terminology, we have switches which implement forwarding. They forward packets. These switches are configurable through rules, and these rules are computed by controllers. The controllers themselves rely on two pieces of information to compute rules. Policy, which tells you what the administrator wants, and then network state, which tells you what's going on with the network. So what links are available, what links are down, what utilization you have, et cetera. So given this, how do we build controllers? So the earliest answer to this was what we call single image controllers. These are things that run on a single server. And examples of this are Nox, Pox, Roux, and other things that you might have heard about before. And so the idea here is very simple. We have a controller that observes a sequence of events. So an event here tells you something happened in the network. And it uses this sequence of events to compute network state. So basically, if you see a link failed event, you know that a link has failed. And applications, so the things that compute rules, react to these events and come up with updates. Now, the events themselves are sent, the events themselves are sent over TCP. So what this means is that there's no reordering of events from the same switch. But if you look at events from different switch, they're allowed to be reordered. So in this example, we have event 0 that happened before in switch A, followed by event 1 in switch B. But as far as the controller is concerned, event 1 shows up in the controller before event 0. And that's fine. Updates can also be reordered, and this essentially comes down to the fact that if the controller computes two updates, the order in which they're applied, it can be different from the order of computation. So, and people have dealt with all of these problems before. So the question eventually becomes, how do you deal with things like controller failures, or how do you scale controllers? And the answer is, let's move to distributed controllers. But then we go back to the original question, how do you build distributed controllers? So why is this any harder than building single image controllers? Well, the problem is that event ordering can now differ across controllers. So two controllers might disagree on the order in which events happened in the network. And we need to make sure that the rules that they compute converge despite this disagreement. So there's two ways you could do this. The first is you could build algorithms that basically are correct despite any reordering across events from different switches. The second is you could use mechanisms to ensure that controllers will eventually agree on ordering. Now, if you think about it, the first one is obviously less general. You have to change all your algorithms. It's a pain. So everyone sort of goes on this idea of let's rely on some ordering mechanism. So then the question is, how do you implement event ordering, or how do you get people to agree on ordering? The answer generally has been to rely on mechanisms called consensus protocols. So let's treat consensus as an oracle for a moment. The idea then becomes that you can think of any controller as consisting of a framework part and an application part. When the framework receives events, it queries the oracle, asking it what order should it deliver the events in. The oracle decides on an order, and it sends it back to the controller, which can then basically process these events in this order. Now, since everyone agrees on ordering, the results should be the same. And what this means is you can continue using the algorithm you were using for single image controllers. And this paradigm is quite common, and in the distributed systems literature, it's commonly called replicated state machines, and it's used for all sorts of things. And this has also been pretty widely adopted for SDN controllers, so Onyx, Onos, and others are essentially RSMs at this point. OK, next question, how to implement consensus in the first place. Now, there's a very rich literature on this. I'm not going to try to explain to you consensus in great detail, but just to explain the problems, here's a quick overview. So basically, in SDN, it's commonly been done using existing approaches like multi-Paxos or Raft or ZAB, which is Zookeeper Atomic Broadcast. The basic idea is these mechanisms appoint a leader. And the leader is the one who receives network event and is responsible for deciding on the ordering. So if the leader receives events in event 1 followed by event 0, that's the ordering we will all deal with. But because the leader might fail, it replicates these events to other controllers. Now, and to ensure that failures don't lead to any problems, it actually waits for a quorum of these replicas to confirm that they have replicated these events. And this quorum is typically a majority, but you can play around with the quorum size and with various trade-offs. Now, once a quorum has confirmed delivery of the events to the applications, the leader sends it to its application, which computes the rules and installs them on the switches. Things are good. Now, what happens if the leader fails is that the protocol has a mechanism to appoint a new leader. And the key component here is that you make sure that the way you appoint a new leader ensures that you don't forget the order in which events were processed. And because you have this quorum, you can find you have this nice intersection property, and you can elect a leader who remembers the order in which events were received. And if there's any state that needs to be reconstructed, you can reconstruct it by playing back those events if necessary. So this is the canonical mechanism, but it has some limitations. So the first one is fault tolerance. So when your network partitions, at least one of your partitions must cease to function, because this is just a result of the quorum property. There's a problem with scalability. As you increase the number of controllers, these consensus algorithms typically start having larger and larger latencies. And finally, due to some very fundamental results from distributed systems, the performance of these, that is the number of rounds it takes before they agree, is sensitive to things like message losses and message latency, at which point you really are placing some very severe limitations on the control channels that you want to use. Okay, so given this, what our paper tried to look at is consensus really required in this environment? Like, could we build SDN controllers that are correct, programmable, et cetera, without calling upon consensus? So to address this, let's first investigate what is the assumption consensus-based controllers are making. So the basic idea is that network state, which is what are the rules in the network, what links are up, what links are down, et cetera, is something that resides in the controllers themselves. So because you have this assumption, the obvious thing is you need to make sure that this network state cannot be lost. And so replicated state machines are just a way to make sure that that's the case. And this is pretty much the exact reason why they're used for things like key value stores. You make sure that the value associated with the key should not be lost. But the thing is, what happens to our packets really depends on the rules and the rules that are installed in the switches and the links that are up. It doesn't matter what the controller knows. The controller can decide that the packet is going a particular way. If there isn't a rule in the network, it doesn't matter. So given that the truth resides in the network, why can't we just query the network to figure out what the current network state is? And this means that it's probably safe to lose network state. You can just go ask the network for it. So here's an alternative way to build distributed controllers. Let's assume we have controllers that all agree on the policy. So they all agree on the rules that they want to compute given some network state. So then what we have each controller do is periodically it asks the network, hey, what's up? What rules are installed? What links are up, et cetera? What is your utilization? And then it uses this state to compute updates. And once it has computed updates, it can just install these updates. So updates here basically say, is the current state of the network any different from, or are the rules in the network any different from what I'd like them to be? And if so, here are some updates for this. And the thing is, if you make some standard assumptions about controllers and about the network, which is you assume that the network is quiescent eventually, and so it isn't constantly changing, this will converge. And by the way, this requirement of quiescence is not unique to us. Every network protocol that people have discussed in the last, 30 years have required quiescence. Otherwise, we really wouldn't have functioning networks. So this is one approach, but there are some challenges with it. The first is, how do we actually write control applications that work in this model? The second is, can we actually have our programming model continue to support the event-based applications that we're used to? So there's perhaps some body of SDN control applications out there. Can we continue to use them? There's an efficiency problem. So every time you query the network, the amount of state that is being returned might be huge. Can we make it more efficient? Can we minimize the amount of traffic being sent? Can we preserve some really critical safety properties? So can we make sure that, for example, you don't take certain paths that would cause the world to end for some reason? How do you update policies? I said we assume that everyone has the same policy. Eventually, policies change. How do you make sure that that's not a problem? And of course, are there classes of policies that don't work with this system? So all of these are answered are addressed in the paper, though you have to sit through the appendices, so it's 17 pages rather than the 12 that you might like. But in this talk, I'm only going to address the first 3. So to start with, let me describe a system called SCL that we've built that addresses many of these questions. And then based on the architecture of SCL, I can explain how these things get solved. So for SCL, so this is just a figure of what SCL looks like. We basically build on standard single image controllers. For our tests, we used POX as our single image controller. And we replicate them, so we run multiple copies. We add some code to both the switches and to the controllers. On the switch side, we add agents that are responsible for implementing the ability to query for network state. So by default, OpenFlow doesn't give you an easy mechanism to do this already. And also, they build a certain kind of control channel for us, which I won't talk about in this talk. And this is not a ridiculous thing to implement because most OpenFlow switches have an OpenFlow agent. We're just expanding it by a bit. On the controller side, we use proxies. These proxies basically interpose on the communication channels to the control application, and this implements all the mechanisms required to ensure convergence. And I will spend a lot more time talking about the proxy in a couple of slides. OK, so this is our model. What are requirements we place on the control application? We require that the control applications themselves be deterministic. And what determinism here means is just that given the same network state, you should compute the same set of rules. Don't use random numbers. We need them to be idempotent. So if you're given the same network state multiple times, you should be able to compute rules multiple times. You shouldn't be saving state or something that would cause you to crash because you've had to compute things multiple times. For this work, we assume proactive applications. So proactive applications are these applications that don't deal with individual packets. They actually install rules down and set up paths on the network. This is actually the commonly deployed. This is the most commonly deployed configuration for SDN today. And finally, we assume that there's a mechanism to trigger updates. So basically, trigger the application to recompute rules. This falls out quite easily once you have the first 3 of these conditions met. OK, so now that I've given you these requirements, let's look at what the proxies do. So the idea here is very simple. Each proxy maintains a log of all prior network events that it has seen. And yes, if you're worried about this log growing in an unbounded manner, there's stuff in the paper about how to do compaction of this log. Just assume that it's possible. So now all switch events are sent to all proxies. So whenever a switch has an event, it broadcasts this message to every controller or every controller proxy. The proxy immediately takes this event and all of the prior events it has seen and triggers recomputation. And the computation itself is assumed to be based on the sequence of events that the proxy is telling the application about. So whatever the proxy says, the application uses that to make its computation. And the controller then generates an update and sends it to the proxy. The proxy, to achieve efficiency, also has copies of all of the tables that it believes are installed on the data path. So these are not being updated. These are not coherent necessarily. It's just that it knows that this is the rule it has sent, and it can periodically check to make sure they're correct. And these tables allow it to deduplicate any updates. So if you think about it, it just reduces the amount of extra updates that you're seeing being sent. So this is how a proxy works, but the obvious problem is I did not address the original challenge of getting everyone to agree on the order of events. Because remember, we're dealing with event-based applications. The order of events is basically what decides the rules that are computed. But beyond that, we actually have very, very weak failure semantics. We assume very weak failure semantics, so we must also deal with cases where due to failure or omission, one of the controllers is unaware of an event that all other controllers are aware of. We call this agreement, another agreement policy. And the last bit is we actually allow every controller in the network to fail and then get and then come back to life. So we also need to make sure that despite missing multiple events from the network, the controllers are eventually aware of the state of the network. So if they go away, they come back. If the network has had a few link failures or a few link recoveries, they should eventually be able to compute the correct routes. So we address this through the use of two mechanisms. The first is we have a gossip protocol or an anti-entropy mechanism between the controllers. So the controllers exchange information about what events they have logged, and we use this to achieve eventual agreement on the set of observed events. So basically, if I missed an event, but maybe someone out there heard of this event, due to gossip, we can make sure that eventually we agree on the set of events that we have all seen from the network. In the paper, we also build on this gossip mechanism to guarantee that ordering is that the controllers will agree on ordering. You can go read the algorithm for doing this in the paper. However, this is not the only way to guarantee agreement. You could use other mechanisms, such as synchronized clocks using PTP, to do that. The second mechanism we have is one that has the controllers periodically query the network for state. And this basically makes sure that despite failures, the controllers are always aware of network state. Now, to actually achieve efficiency here, we include information in the query that allows the switch agent to decide whether or not to respond to a particular query, which allows us to massively reduce the amount of control traffic. We have results about this in the paper. So that's one way to design controllers which do not require consensus. But then there's an obvious question: why should we abandon consensus? Consensus has served us well for, I don't know, at least since 2010, when the first distributed SDN controller was described. Why abandon it now? The answer is that it's conceptually not clear that it's necessary. So, the RSM assumption, as I pointed out before, says that the truth about the network lies in the controller. But as I've also said since, in reality, what happens in the network depends on what the data path has, not on what the control plane has. So if that's the case, why use this mechanism that's actually quite complicated? But beyond that, getting rid of consensus actually helps improve both performance and resilience. So in terms of performance, it improves responsiveness. This is because when you require consensus, you need at least one RTT of time between the controllers to actually get them to even start reacting to an event. In the SCL case, as I said, we immediately deliver events. You can react immediately, and in many cases, that's sufficient to fix the network. Second, it helps with scalability. I already talked about the fact that you have an increase in latency as you increase the number of participants here. In our case, we don't have any increased latency to respond to events as you increase the number of participants. And finally, it helps with fault tolerance. You need a quorum to be available in the case of consensus. In our case, we have designed our protocol to be functional as long as any one controller is connected to a given switch or a given partition. So the failure requirements are much weaker. So finally, getting rid of consensus might have some performance implications. So let's quickly look at what happens with route convergence. So it's commonly believed that if you didn't have this sort of coordination, routes should converge slower. What this graph shows you is that in an AAS, SCL allows routes to converge about 8 times faster. The reason is that for most failures, any one controller responding to it is sufficient for patching up the network and getting you paths back. And we see that this result also carries over to the case of data center topologies like factories. Finally, we also care about convergence. We want our network to stop changing at some point. And to measure that, we looked at when does everyone, so the network and all of the controllers, when do they agree on what's happening and what should be done? And you can see that, again, SCL actually does better than the consensus mechanism. In part, this is because by letting all switches communicate to the controller, we can often beat out the time it takes to have the controllers learn about this through the consensus mechanism. And again, this follows through in both data centers and ASs. So I've only gone over some of the results that we have in the paper here. We have actual proofs that the gossip and periodic update mechanisms are sufficient to guarantee convergence. We use broadcasts for our control channels. We use in-band control, so we describe that in the paper too. And we describe, of course, mechanisms for policy updates and how we interact with other policies. So quickly, in terms of related work, people have done a bunch of work on control plane consistency. The original ones were on using consensus to achieve serializability. This is what both Onyx and Onos did. We've recently seen work on using atomic registers. So OpenFlow switches have grown in power. They now support atomic registers, which have compare and swap capabilities. So people have been looking at using that to provide these semantics. And more recently, people have also looked at providing much stronger semantics, like exactly once event processing in systems like Raven. There's also been a long line of work in data plane consistency. The idea here is that because updates can get reordered, you don't know what set of rules your packets are being processed through. This, of course, is orthogonal to our work, and we make use of this, but you can look up this work if it's interesting. So finally, in conclusion, the conventional wisdom so far has been that when you build a distributed SDN controller, you need consensus, and you shouldn't get rid of consensus because you'll be wrong or you'll be slow. What I've shown you in this talk is that you don't require consensus. You can get correctness for existing single image controllers without any use of consensus. And in reality, not only does this simplify controllers, it actually improves convergence times. It allows your network to be much more responsive to failures, and it improves robustness. And with that, I'm happy to take questions. Thanks. Yeah.
Shenker from AT&T Labs.
Hi.
I see that removing consensus by having a distributed control plane is kind of really a cool idea, but you have conveniently sort of sidestepped the chattiness of control protocols, right? The control plane is already overwhelmed with the number of messages that it doesn't scale the data plane beyond a certain point. But now you're sort of having this replicated control system that makes it even more chattier. You have made the control plane problem even worse. So do you have any thoughts on that?
So in this talk, in part because of restrictions on time and also page limits, we mostly focused on replication. If you are worried about what happens as the data plane scales, how you should scale up controllers, sharding is a perfectly reasonable way to do it. And there is prior work looking at how to shard and have limited consistency and still get good performance.
I was actually asking an orthogonal question in
Sure.
terms of the chattiness of the control protocol itself, right? So the more control messages that you have, the control plane is going to be all the more busy, right? And by having more controllers and sort of doing this mechanism of...
Sure. Sorry. OK, that makes sense. Sorry. So it's a great question. Of course, we increased the amount of control plane chattiness. In our evaluation, for a bunch of scenarios, we found that we were using less than 10% of a 10 gig link. So we were using about 100 megabits. So we didn't see it in practice, but it's a good question. There are ways to solve it that I can come up with. The problem is there's a balancing act. Every time I try to reduce the amount of control plane messages, I start getting into something that looks like coordination. So I can appoint leaders, or I can appoint, like, there are, the benefit of a leader is only one person produces a message. But then, of course, anytime there's a failure, responsiveness goes down. So there's a trade-off there that we just have to explore.
OK, thanks.
OK, one more quick question.
Yeah. Hi,
Sure.
Mohsin from Tufts.
Hi.
My question is that the conventional distributed controllers like Onos or Onyx, they are following the logically centralized model, right?
Mm-hmm.
And it seems like your model is not sort of providing an abstraction of a centralized model to the upper layer. For example, in the case of NFV orchestration, if we have to integrate SDN module into the mano layer, so how do you see that your model would fit in? So
for the particular example that you asked for, our policy update mechanism takes care of that.
Right.
I think we would claim that we do provide a logically centralized model. Some of the authors of this paper were involved in writing the original description of logically centralized, but I don't know. If you can give me a specific example of where it doesn't work, I can tell you how we would fit it in. The question as such is very broad otherwise.
Right. Maybe we can talk after the...
Of course.